hit by the ball or whatever.
All right, I'm starting the lecture. Well, since you just mentioned Arduino, you just got my neurons, fired up already. So I'm blaming this on you.
That's all right.
So I'm gonna have to show you guys a very short video. I'm not gonna show the entire thing because it's gonna take a little bit too much time in this class. And that was a guy who was selling passes to paintball games in the previous class, but he's not showing up in this one. I don't know why. But it's always the same guy at the end of the spring semester at exactly the same time, showing up and saying, "Can I use like 2 or 3 minutes to sell tickets or passes to a paintball place?" And of course, I hijacked that opportunity to show people the automated paintball machine, the Paintball Sentinel. Okay, so let me find that link first, because I thought this is a little bit related to this class because it is low level kind of programming. And here's the link. And I need to enable the audio. Devices, crank it up, there we go.
Hello and welcome to Frank Plan Video Network. I'm Frank TV and I will be your host today. We're here in Ames Garage filming our second video in a series we are doing on working with the Arduino microcontroller. In this project, we're going to look at controlling servo motors with buttons, and then how to run multiple buttons from a single root. Before we get started though, I'd like to introduce team member Frank W., who will be helping us out with the graphics and code today. Frank, how are you? Hey, thanks Frankie, I'm great. Excited to be here and ready to go. Hey Walt. All right, Frank. Okay, here is our list of materials. We will be using 5 servos in this project.
So I'm going to kind of skip forward a little bit here. So this is the code in Arduino, which is kind of a C++ programming environment.
Each servo, one in each direction. Then wait for a button. And perform the movement while the button is being pressed. If we switch to camera view, then I will try to demonstrate. Okay, if you pretend my elbow is a servo, when you push a button, it moves up. Push another, it moves down. Same thing with the shoulder, up, down. Now, we want to add a fifth servo, but all digital pins were used. So we decided to try and move multiple pins to a single analog pin using the voltage value, thus freeing up the digital pins for future runs.
Okay. So I'm just going to show this much. The guy who did this, he's working in the lab, is Daniel. Do you know who's Daniel who works in the lab? He's kind of like a tall but older gentleman. He's a lab tech. Not a lab tech, he's actually an IA, an instructional aid in the lab. And he did it all by himself. He didn't ask for any help. He took Visual Basic some time ago, but he's definitely learning a lot of programming on his own, to the point where he can put these things together and also write the programs to kind of control the whole thing so that the robot is basically running the show. Yeah, and these are all run by servos, and I think when he said servo, I think he meant RC servo, which are not very expensive. They can go as inexpensive as about $12 each. But they have a lot of torque, okay? They don't have a lot of precision, but they have a lot of torque, and you can control the position relatively easily using a digital signal. Like something with an Arduino board or a Raspberry Pi, you can control these things pretty easily. So you can put together your own project, your own robot. It's a lot of fun. Okay, so for the summer projects, this is something that some of you may consider. Okay, so I just kind of want to mention this. The exam 2, the solution is online. Okay, I streamed that out, on last Thursday. So if you're kind of curious about the right answers and whatnot, just watch that video. It's unless you're in that particular class already. Okay. So Scott, did you watch it in Italy?
No.
Ah, okay. Because at the end of the video, I said, okay, hello, Scott. Because I was thinking Scott may actually watch it, in Italy.
I was super busy.
That's okay, understood, not a problem. Okay, so what we'll do today is I'll give you a new homework assignment. But the due date is not right, okay? So I'm gonna give you guys at least one more week to get this done because this is one of those things where it's a culmination of everything that we're gonna learn in this class, okay? So it is really good to take a look first so that you know what the homework assignment is about. And then when we talk about the concepts in class, then hopefully it will click and go like, oh, okay, so this piece belongs here in this homework assignment and so on. So let me go switch to the other class. 310 right here. So this is going to be the second last semester using Moodle. So fall is going to be the last semester because starting spring 2018, I'll be using Canvas in my own way. So inside subroutines, which is where we are, where we should be at this point, is the homework assignment. And the homework assignment is to implement Fibonacci numbers using the toy processor. Okay, I picked Fibonacci because it is not too complicated, but yet it is not too simple. It is not like factorial where you can do it easily without having to apply the concepts that we have to learn in this class. So this one does require the use of the concept that we learned in this class. But it's not too complicated at the same time where it is not doable. Okay, if I were to ask you guys to write a binary search tree algorithm to construct and traverse a binary search tree in assembly using the toy processor, I'm not going to do that. Okay, with the i386 assembly, it's actually pretty easy, but with a toy processor, there's no way that you can do it realistically. Okay, but Fibonacci is one of those things where, man, you can actually do it. Okay, so we'll go ahead and take a look at Fibonacci numbers itself. This is a hyperlink to the Wikipedia page on Fibonacci. You can read it up. You can just copy as much code as you want from this page, which is only this part here basically. Okay, it's a recursive definition where there are two ways to provide the seed values. You can start with 2 and 1, which is what I would do. You can say f of 2 is 1 by definition, f of 1 is 1 by definition. And then for everything else, if n is more than 2, then you say f of n is f of n minus 1 plus f of n minus 2. Okay? So it is recursion, but it is not simple like factorial. Factorial is easy because there's only one recurrence, but this one has got 2. So that makes it kind of a little bit more complicated, and you cannot just do things in a particular way, which is you cannot make it very simple. Okay, you have to use local variables and stuff like that to get this done. Okay, so are there any questions about what is Fibonacci number itself before we kind of move on and talk about the concepts that you need to know to get this done? Okay, no questions? All right. So I'm going to stay on this page for a little bit, and I'm going to write a program in C to get this done first, because we definitely want to look at the logic of a program written in just normal C and just get to see it work. Okay, so here's Fibonacci number. It returns an unsigned, okay, because all of these numbers, none of these are negative. I can use unsigned. So f of n. And with any type of recursive algorithm, the first thing you have to say is, when do we stop? Okay, I always ask that question first. Okay, when do we stop? Well, in this case, we have 2 ways to stop. When n is 2, we stop. When n is 1, we stop as well. So we say, if, okay, I'm not gonna optimize the code at this point. If n equals to 1, then we know the answer is, okay, so we say unsigned result. Okay. So in this case, when n is 1, result is going to be 1. Else, when n is 2, result 1. And then we have this else here, which is going to be the recursive one. So the recursive one is saying the result is f of n minus 1 plus f of n minus 2. And at the end, we say return result. So are there any questions about this particular implementation of the Fibonacci numbers? No? Okay, so that's fairly close to the actual definition on the Wikipedia page. Okay. So when we want to test this particular algorithm, we just have to provide a main shell and give it a number to process. Now, if you want to be fancy, you can do something like this. Okay, so we can supply argc, which is the count of arguments, and then we supply const char star argv in square brackets, which is an array of strings, and each one is a parameter to the command line. I think we briefly talked about this before in this class. Okay. Now this part, obviously, you do not have to do it in the assembly implementation using the toy processor, because the toy processor doesn't have any input-output capabilities. So given this, we can say if argc is greater than 1, which means we have one extra thing that is provided, which is the number that we want to process, then we go ahead and do the following. And then we need a way to convert that number into an integer. So I think it is ATOI, okay. And we are converting, so I'm gonna do it step by step here. We have a local variable n is ATOI, which stands for ASCII to integer. And the string that it is working on is argv1, because we have at least 2 arguments, so we're using the second argument as the number. And then we just want to do the computation. We just say f of n. Here we are not even storing the result of f of n. Now if you want to store that, we can store that just so that we can see what it is. So we have variable r here to store the result of that. And ATOI probably needs to use a pound include. So let me go look up what pound include we need to use here. stdlib, standard library. Okay, so we will use that. stdlib. There we go. And this is plain C. It's not C++ at all. It just gets the job done, and that's all I care. Is that okay so far with this program? Okay, so I have a simple program that takes in a number that I type on the command line, and it will do the computation, but it's not actually going to print anything. It's just going to store the value in R. So I just want to see if this program works. Okay. So we gcc-g, because without the debugger, it doesn't show anything. So we got to remember to do a -g to include all the debug information. -o, specify the name of the output file. We just call it f itself, f.c. Now, if I really want to double check things, I would include -warn all, and also -pedantic. So this way, I can make sure that the program doesn't have any hidden issues. And the only issue here is it says variable r is set, which means I store something into variable r, but I never used it. That's okay, because I'm not printing anything in this program. So that's fine. So we say gdbr, which is the name, gdb f, which is the name of the executable. When we run the program in the debugger, we can actually supply the second thing. So we can supply the number that we want to compute the Fibonacci out of. But this is not going to do anything, because if I just press the enter key, it will go through the computation, but since the program does not output anything, it doesn't show us whether it is computed correctly or not. Okay? So what we need to do is to set a breakpoint. And depending on how much time you want to spend on this, we can put a breakpoint just on line 26 and just say, okay, what is R? We just want to make sure that it is the right value. So now when we run the program, it will stop on line 26, and then we can either single step into it and see all the recursion happening, or we can step over it. And I cannot remember how to step over. To step into is step, which is S, and then to step over is something else. But I can put a breakpoint. Oh, I cannot. that presents a little bit of a problem. So if I don't know how to do something, this is what I do. We say help, and then we know that we are dealing with stepping or how to navigate from one line to another line. So that would be in running. So now we can look at these things. Next, there we go. So next is the command that we need. So I just type n, which goes through, which will get into the subroutine but not trace into the subroutine. So it's going to execute the subroutine without getting into it. So now I'm ready to return. Unfortunately, I cannot print R at this point because it is not in scope. Darn it. Okay. I have to change the program and reposition things a little bit to make that work. So the quick way to do it is to put R all the way out, so it's not limited into the inner scope. Okay. So we rerun GCC, rerun GDB, and do the same thing. Find a good place to put a breakpoint, line 28. Run the program with 6 as the argument. So now in R, we should have the Fibonacci number of 6. And according to this, it should be 8. So when you look up here, and it does show you the sequence for the first few. So this is 0, 1, 2, 3, 4, 5, 6. So it is in fact 8. So 8 is the correct answer as the Fibonacci number of 6. Are we doing okay so far with this program? Okay, yep.
So what is ARGC and ARGB in the program?
Oh, those things, they are useful, but only when you are writing a program in C, C++, and I think Java as well. Okay, so ARGC is telling you the C stands for count. Okay, it tells you the number of arguments being passed on the command line in order to start the execution of this program. It's always at least one, which is the name of the program itself, but if you type anything after the name of the program, those would be like 2, 3, 4, 5, and so on. Is that okay? And then ARGV is an array of strings. Each one is corresponding to the items on the command line when you start this particular program. So it's kind of handy, but they're not necessarily useful in your project. Okay, for this program, I just makes it easy. So this way, I don't have to recompile the program to try the Fibonacci number of 2, the Fibonacci number of 20, and so on. It just makes it more convenient to test the program. Okay. All right. So now the key is, I gave you the code already. Okay, this is your homework assignment. Your homework assignment is just doing this. Okay, but in assembly code using the toy processor. And in previous semesters, there were people who figured out a switch in GCC, which is dash uppercase S, and it will make the compiler spew out assembly code. Which means they don't really have to do all the work manually. Okay, most of the time people don't cheat. Okay, they look at the code generated and they get inspirations instead of how to proceed. What instructions to use. But with a toy processor, it's not going to be very helpful, unless somebody in this class decides, I'm going to take on this challenge and rewrite the back end of GCC to crank out your opcode for the toy processor. Well, for those people, I'm going to give you an A anyway. All right, so now the key is, how do we do this? Okay, in other words, in this case, we have a parameter, and we also have a local variable. Okay, the local variable is not that big of a problem because for those of you who say I can just return in the middle of a conditional statement, yep, go ahead. Okay, so you can just say return 1 instead of result equals to 1, so you don't actually need to store the value into a local variable first. But n is a problem because this is a recursive subroutine. In other words, when you do the first recursion, which is here, if you just say that, hey, I can just subtract a register or some place static in order to compute f of n minus 1, that's not going to work. Because at some point, that invocation is going to return, and then the second invocation needs to deal with n minus 2. But if you destroy the value of n in the process, then you won't be able to figure out what is n minus 2. So you have to keep the value of n in order to successfully call both of those invocations correctly. Is that okay? Okay. So the problem now is, where do we store a parameter then? A stack. Very good. Okay, so we can store the parameter on the stack. Because that way, for each invocation, it has its own n, and they won't interfere with each other. Does that make any sense? Okay. So to illustrate it, one thing we can do, even in this particular setting, which is using the this is using the 64-bit AMD instruction set. But even so, we can still see it. Okay, even in the program, in the C program, we can still see the effect of using a stack to store a parameter. So this time we are rewriting the program, but we are putting a breakpoint at the entry point of f. Okay, if you're using GCC and you just want to set up a breakpoint at the entry point of a subroutine, just B and then the name of the subroutine will do it. Okay, so it's pretty convenient. And now we will run the program. Okay, I'm not going to make this too brutal, so we'll just say R4. Okay, we're trying to find the Fibonacci number of 4. Here we go. This is the first point, the first invocation. You can see that GDB is telling you this is the invocation, n equals to 4, but I'm not interested in the value of n. I'm interested in the address of n. Where is it? Okay, a whole bunch of 7f, blah, 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 blah. So we only have to pay attention to the last 2 digits, or last 3. It's 19C in this case, okay? And then what I do is I continue execution, which means we'll continue execution until we hit the breakpoint again. This is the second invocation. The second invocation is trying to figure out what is n equals to 3. So we say, what is the address of this n? They're not the same, okay, which is good, because if they are the same, then we might have a problem. They're not the same, and how are they different? They're off by 40 in hexadecimals. They're off by 64 bytes on the stack, which is a lot. Okay, but since we do have a lot of memory on these modern computers, it's not a big deal. Okay, but we also can do this. Okay, I think I have shown you guys this before. BT or backtrack. So when we use BT, we can definitely see that this is the second invocation of f, because we have one invocation directly from main, which is the #1. This is the second invocation, which is the recursive call. The recursive call from which line? Well, from line 14, which is inside the function f itself. Okay, so BT is very, very helpful to show you, how a recursive algorithm works. Okay. Well, since the value is 3, if I continue, it will go to n equals to 1, which is going to be the last the last invocation in this particular chain of recursion. So if I do BT again, we can see that this is the third invocation, and we can also see the value of n of all the previous invocations. Is that okay? All right, okay. Now we have already shown the value or the address of n with the previous 2. Well, might as well look at this one. It is 11C. How does that relate to the other 2 locations of n? They're off by 4 zeros. Okay, so once again they're off by 4 zeros. But in which direction are we changing? They're decreasing. Very good. Okay, very good observation. And with a stack, as we have more stuff on the stack, how does the stack pointer change? To lower and lower and lower. Okay, very good. So from observing the address of a parameter in a regular C program without even dropping into assembly language, we can kind of see that parameters are stored on stack. Okay, and this is how it can maintain multiple invocations without any interference. Is that okay? So we want to replicate this kind of thing in our program. All right. What about result? What do you think? The address of result, how do you think it relates to the address of n? And do you think result is also stored on stack? Well, let's find out. Okay, so the first thing is find out. We can just say print the address of result. Okay. And what is that showing you? Okay, it is 2C, which means it is actually pushed, or it is actually reserved before n is reserved. That part is kind of strange. How do we get to the result of previous invocations? In other words, if I use BT and I say, oh, I want to find out what is the address of this invocation of f. How do we do it? And we talked about it once. I'm not sure how many people remember that. There's a command to do it. Frame. Okay, we use the command called frame. This is frame 0, which is the current invocation. This is where the execution point is. But if you want to go back to an earlier invocation, you can just say frame 1, or frame 2, or frame 3, depending on which frame you want to go back to. So if you just say frame 1, we're going back to that particular invocation. This is the call that is triggering the last invocation of f at this point. So what we want to do is to say, oh, I want to know the address of this particular result. Print the address of result, and it is 16C. Okay? Do you see a pattern here? The difference or the distance between n and result is always the same. Okay? Because in this particular frame, n is located at 15C, and then result is located at 16C. They're only off by 10 or 10 in hexadecimal, 16 bytes. Okay. What about the other frame? What about frame 2? Let's go there. Frame 2, we want to look at the address of n. We want to look at the address of result. And they're off by 10 bytes as well. Okay? Well, this is the concept of a frame. A frame is basically something, a chunk of memory on the stack. But the structure of this chunk has there's a particular structure to it, and it relates to your parameters and as well as your local variables. They become a part of the frame. The frame itself is stored on stack. And there's one frame per invocation, not per function. Okay? It's very important to separate those concepts, or to distinguish what is an invocation and what is a definition of a function. An invocation is a runtime thing. It's a dynamic kind of thing. At any point of the execution of the program, I may have 0 or any number of invocation of a recursive subroutine. But definition is what you see in the source code. There's only one definition of f. Is that okay? So the definition of f is kind of like an operation manual. It describes what to do. But who's doing it? Maybe nobody. Okay? If f is not getting called, nobody's following the instruction. On the other hand, if we have a recursive subroutine, then we have multiple people actually executing that instruction, except they cannot be working at the same time. Is that okay? All right? Okay. Yep.
So how big is stack and how many values can you hold if here it holds all values?
I think we answered that question before by using a endless recursion program and compare the stack pointer from the beginning versus the end. But we can do it again. Okay? So we'll go ahead and look at this program. How big is the stack? Self-documentation. Documentation. So we're going to write a program that is recursive and is endlessly recursive. How's that? I think that would do it. Okay, so we'll go ahead and try to run this program. GCC-G-O, how big is the stack? There we go. And then we GDB the program, HBits, put a breakpoint at main, run the program. This is the first instance. So we say print is not as good. IR, this is the 64-bit version. I cannot remember the name of the stack pointer. RSP. Okay, there we go. So IR IR stands for info register. It's just asking what is the value of this particular register. It's FE1E, as the last few digits. FE1E0 as the last 5 digits. So if I continue execution, I will delete my breakpoint first. D1 deletes the first breakpoint, which is my only one. And if I continue execution at this point, the program is going to do the recursion endlessly until it runs out of stack space and then cause a segmentation fault. Like that, okay? So at this point, I can do another IR RSP, and it ends at this point. So when you subtract these two numbers, then you know the size of the stack. You can basically just say print 0x FF, it is 7, so it's basically FFE1E0 minus 0x 7FF000, and the answer is about 8 megabytes. So a normal program in this particular configuration of the kernel is given about 8 megabytes of stack space. Now, how many times can you do recursion? Depends on how big is one frame, okay? If you do not use any local variables and there's only one parameter, you can do a lot. On the other hand, if you have a huge, big data structure as a local variable, then you can only do a few. Does that make any sense? All right. So are there any questions at this point about what we have done so far in this class? Questions? Okay. All right. What about returning a value? How do we do all that stuff in assembly language? Okay. So what we need to do is to look at one particular really simple program first. Okay, so we look at this program. I'll just call this 5 because that's what it's going to do. I have a program, I have a subroutine called 5, which takes no parameters. Oops. There we go. And all it's going to do is to return 5. And we have main here. Main has a local variable. Let's call that x here. So x is a local variable. X gets 5, or the return value of the subroutine 5. Okay. So this is a very simple program, doesn't do anything particularly useful, but we are interested in the mechanism. How is that 5 as a return value getting back to x in main? That's the question. What do you think? Well, the return address is only responsible to get back to the assignment statement so that we can finish the assignment statement. And what you were mentioning something about stack. You can store a return value on the stack, but that's a lot of operations, okay? So the convention of a compiler is to use a particular register as a designated return value register. Because it's quick, it's easy, it's inexpensive, and it's great for integers and characters and all kinds of scalars. So for scalars, the return value is actually stored in a particular register. And then in the main subroutine, it will pick up from the register and store the value of that register into local variable x. That's what it's going to do. Okay, so once again, the conclusion of this particular example is the return value of a scalar, which includes chars, ints, floats, doubles, and so on. Those are stored in designated return value registers. And the caller can then just go to the return value register and say, oh, I'm assuming the return value is in this register, and then just use that as the value of that expression. Are we doing okay so far with this? Okay. All right. So that means in order to do your homework, you have to come up with a particular assumption. Okay? So what I'll do is to make your job a little bit easier, and I will give you those assumptions. Okay. So I'm going to add to this and say use register A as the return value register. Okay? So this is important because this is an agreement between the caller and the callee. Because the callee or the subroutine being called has to set a value into that particular register right before it returns. The caller, on the other hand, has to also fulfill that agreement and say that, oh, when I have control back from calling a subroutine, I will inspect this register and use the value of this register as the return value. So this is an agreement between the caller and the callee in order to return a value. Okay. So we'll go ahead, I will save it first, okay? The closing date or the due date right now is May 2nd. I'll give you guys 2 weeks to do it because this is a little bit more involved and the program is a little bit harder to debug, so you will need more time to do this. Okay. All right, so are there any questions at this point about the conventions? Okay, no questions about the conventions? Very good. Let's go ahead and just do some subroutines. Like we'll make one that is easy, finding the maximum of 2 variables. Okay? But we'll do it using all of these methods. So we're not going to cheat and use static locations. We'll use the stack to pass values around and stuff like that. Okay. So we'll do a find max 2. Find max has 2 parameters. We have x and y, and we'll drag this out a little bit. Okay, so we have a result variable, and we say if x is less than y. If x is less than y, then the maximum is y. If not, the result is x. And at the very end, we're gonna say return x. Return result, like that. Okay. So this is what we want to implement. The question now is, as a subroutine, what are we gonna do? By the time the subroutine has control, what can we assume is already on the stack? Is that okay? And this part, by the way, is processor architecture independent, because this is exactly what a program has to go through, regardless of the architecture. Now, int may be 8-bit wide, 16-bit wide, 32-bit wide, or 64-bit wide. Same thing with the return address, but the mechanism will still be the same. Okay. Okay. So when we look at this program, I am going to show this on one side, and then use mousepad on the other side to explain, what we can expect as a label of find max. Okay. So in just about any assembly language, you use find max : to define the label as the entry point of this particular subroutine. That part is pretty much universal across all assembly programming languages. So the question now is, what can we assume at this particular label? Okay, I'm going to use / to indicate comment. Some assemblers would use the £, or some other would use the semicolon. But since I'm going to be consistent with my own assembly language in the spreadsheet, I'm going to use //. So right here, I'm going to say, okay, what is on the stack at this point? I just got control. What is on the stack at this point? Okay, so we know several things. So the order is not important at this point. Okay, so we know that the return address is on the stack. Okay, is on the stack. What else do you think is going to be on the stack? The parameters. Okay, so that's good. So we say parameter x is on the stack, and parameter y is also on the stack. Very good. Okay, indeed, these are the 3 things that are guaranteed to be on the stack. Okay, very good. But then the important part is the ordering. Okay, what is going to be the ordering of these 3 things on the stack? Well, let's think about this a little bit. Okay, so there are only, I just taught 440, so we just talked about permutation. Okay, so out of 3 things, if you choose 3 things out of 3 where ordering is important, how many ways can you arrange those things? 3, the permutation of 3, choosing 3. is 3 factorial, which is 6, okay? So we can actually just look at all the 6 permutations and go, does this make sense? Does that make sense? Does that make sense, okay? I wouldn't use that line of reasoning a lot of times, but this time we can, okay? So we'll go ahead and take a look at those particular combinations. There are only 6 of these, not a big problem, okay? So we can have the return address being the highest, X being the second, Y being the last, okay? We can have X, Y, return, and we can have, but the other ones do not make much sense, you know, so I'm inclining not to talk about something like that, where the return address is between the parameters, you know, that just doesn't make any sense at all. So we won't focus on these, okay? Is that okay? Because it just doesn't make sense, okay? But then we still have something else like return, and then we have Y, and then we have X, and then we have Y, X, and then return. So we'll just consider these 4, okay? And see which one makes more sense to us. In other words, do you think, okay, this is higher memory address, this is lower memory address, which means the return address is saved first in this case, and then X is put on the stack and then Y is put on the stack. This one is putting X on the stack first, putting Y on the stack second, and then return address put on the stack last, and so on. So which one do you think is more reasonable? The top one? Well, the top one, we can do it in this class because we do not actually have a call instruction. But remember what a call instruction does. Do you guys do remember from the previous class? Okay, no, maybe not. Okay, that's okay. So the call instruction, which is responsible for calling a subroutine, is actually doing several things. Okay, do you remember how many things a call instruction has to do? There are 2 main things it has to do. The first one is to save the return address, okay, which is the address of the next instruction. Okay, so I'm not going to use the assembly code here, and I'm just going to say, you know, the call subroutine. Let's say call findMax. Okay, so the instruction call findMax, which is going to call the subroutine findMax, is going to do 2 distinct operations. It will first have to save the return address on stack, and then what is the second thing it's going to do? Well, that's part of the save, you know, address, save return address. So it has to decrement, store. Okay, so we'll separate this into 2 steps. Okay, so we'll say decrement stack pointer to allocate space, store return address to allocate space, and then what do we do? When you call a subroutine, what is eventually what's going to happen? No, not yet. Well, the call instruction doesn't do that. So it will just transfer control. It will continue execution at findMax. Okay? Okay. Say that one more time.
It's gonna set the program counter to the location of findMax.
Right. It will change the program counter to the label findMax in order to continue execution in findMax. Hold on a second here. But if the call instruction is doing all this stuff, who's going to put the parameters on the stack after the return address? No one. Okay? Because the call instruction is going to do this as the last operation, it means it is impossible to do it this way or to do it this way. Is that making any sense? Because by the time we have the return address on the stack, the program would have continued execution in findMax already. The caller does not have a chance to put X or Y on the stack after the call instruction. Okay? Now with our toy processor, we have a chance because we do not use a call instruction, we use individual instructions to implement the call. So we actually get to choose. But with a cisp architecture and also many of the RISC architectures, call is one single instruction. It combines the decrementing of the stack pointer, the storing of the return address onto the stack, and the eventual jump to the subroutine in one single opcode. You cannot separate those three operations. And as a result, we cannot do it this way. This is impossible, because in order to do it this way, the caller still needs to have control after pushing the return address on the stack, and then say, oh, by the way, we also have two parameters, x and y. But by the time you're done with the call instruction, you're already in the subroutine. The caller has lost control already at that point. Okay? Is that okay? Does everybody understand why that combination does not work? Because the higher the address, the earlier you have to push or put it on the stack. So this is not possible. This is not possible either. So I'll just go ahead and erase this, okay? And let me just double check to make sure this is all recording. Yep, it is still recording with sound. That's good. Because it's good to check occasionally. And oops, we need this and one of the terminals. I cannot remember which one. That one. There we go. Okay. So we can just erase this one because it's not a good combination, and erase this one for the same reason. So now we have these two left. One is to store x first, store y second, and then do the call. And then the second one is to store y first, store x, and then do the call. So between these two is a tough one. It's a tough choice. Okay. One is how Pascal does it, and the other one is how C does it. So both of these are used, except one is used by C, the other one is used by Pascal, but there is a reason why C is using one particular one. And it has to do with a particular type of function that you probably have not been exposed to. So I'll just kind of give you an idea of what it looks like. Okay. So I'm gonna switch back to here, okay? So instead of just doing find max here, I'm gonna do a find max n in this case, and it's just going to be have an n here, and it has dot dot dot. This is actually valid syntax in a regular C program. So the question now is, what is dot dot dot? I mean, how many people have some exposure to this type of function definition? A little bit.
Not in C.
Not in C, but in Ruby?
Yeah.
Okay. So Ruby can have.
Is it like an array of parameters, or?
We don't know what it is. You can only make assumptions. Okay. So that's the whole thing. Yeah. And you took by 360, right? Okay. So that's why you kind of have some exposure to this. So the rest of the class probably have not seen in your 360 class something like that. Okay. So let me show you what this, okay, so let's just say that in this particular subroutine, we're trying to find the maximum of n, as in, the parameter n is specifying the number of integers after parameter n itself that we are trying to consider. We want to find the maximum of those n integers. Okay, so to understand that, it is probably better to look at how it is called. So we'll go ahead and define the main here. And we'll say int r, which is the result. So we say r is find max n, okay, which means, and then the first thing you have to say is to say, okay, how many things are after the number of parameters, okay, or number of integers that we have to process. So let's say we say 3. Now you have to make sure that there are 3 additional integers after n itself, okay? So we say, oh, here's -1, here is 20, and here's 100. Now, if you want to supply more than that, it's okay, but the subroutine will only consider the first 3, which would be the -1, the 20, and the 100. Is that okay? So if you look at how it is called, then you can look at the implementation of find max n. So how are we going to do this part here? Okay, so what kind of tricks in C and C, well, this is all C, okay? C++ adds on top of C. This does not require C++ concept, okay? It's all plain C concept. Okay, so what tricks do you think would be helpful? Yep.
Well, we know the location of n.
Yes.
And we know the width of an integer in memory.
Yes.
So we could just add that value onto that memory location to get the next one.
Good idea. Okay. In fact, that is exactly what we're going to do. Okay. So I'm going to use I as a variable to control the indexing through quote unquote the array. Okay. But it's not really an array, but I can always treat it as if it is an array. So I'm going to use A as an array, but I'm going to initialize it later. Okay. A is going to be initialized to the address of n plus 1. In other words, when you do quantum arithmetic, it's not just adding 1 to the address, it's adding whatever number of bytes an integer takes to the address of n, and that becomes A. Is that okay? So whatever is after n is now A. So now I can use the usual way of finding the maximum of an array. So we say max equals to A bracket 0. It's just an assumption. You know, we haven't seen anything yet. We're just assuming the first thing in the array is the maximum. Then we use a loop and say I equals to 1 because the first one, or the one at index 0, is already seen. I don't need to look at it again. And we say I is less than n, which is the number of integers that we have to consider. Plus I is as a post operation, so we'll be ready for the next iteration. And in the loop here, the only thing we have to do is to say, if A bracket I is greater than what we already think is the maximum, then we have to update the maximum. Okay, there we go. And don't forget to return max at the end, because if a subroutine is supposed to return an integer and it does not do a return some kind of value, guess what the caller is going to do? The caller will still honor the caller's part of the agreement and say, I'm going to assume register blah 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 is going to be the return value register, and I'm going to use whatever is in that register as if it is the proper return value. Okay? If you don't turn on warning, C doesn't tell you that you're missing a return statement, which can be very, very bad. Okay? It's really bad if it just returns some kind of gibberish value that crashes your program, but that's not the worst. The worst is it returns something that seems to be useful. And the program doesn't crash when it is supposed to crash, and it only crash much later, and you'll be scratching your head because the problem happened like thousands of lines before the observation of something going wrong. Okay? So you always turn on warn all, which the compiler will just tell you and say, hey, this subroutine doesn't look right because it's supposed to return an integer, and I do not see you returning anything in the subroutine. So that's why you always want to turn on the warning in the compiler, because these are problems that can easily be spotted by the compiler. Okay, so are we okay with this particular subroutine and how it gets the job done? Okay, so based on this, which way should we use? Okay, so let me put this side by side to the two alternatives that are left. Okay, find max has two parameters. X is the first parameter. Y is the second parameter. So if we need to be able to do something like this, do we want X to be the parameter with a higher address, or do we want X to be the one with a lower address? Lower is correct. Okay, so the first parameter in C should have the lower address, which means it should be pushed last. It should be pushed onto the stack last compared to the other parameters. Are we okay with that concept? Okay. So now we have only one choice left. Okay, so the stack should look like this by the time we get to find max. Are we okay so far? Well, the stack pointer has something to do with this whole mess, right? Because the stack pointer, after all, has a name of stack pointer. So whatever we do on the stack has to do with the stack pointer. So where do you think the stack pointer should be pointing at, knowing that these are the things on the stack? What is the one thing that the stack pointer always wants to? The last thing that we store on the stack, okay? So it's the last thing that we store on the stack. Which one is the last thing that we stored on the stack? The return address. Very good. Okay, so the stack pointer is pointing to the return address. Now the toy processor does not actually have a designated stack pointer, so we're going to use one particular register for that purpose. And I think the convention that we have agreed on is register D. Okay, so we'll just say that this is also in the toy processor, it's register D, but in most architectures they have a designated stack pointer known as SP, RSP for 64-bit, ESP for 32-bit, and so on. But in our toy processor, we're going to use we're going to use register D. Are we okay so far with this picture? Okay, all right. All right, so we know the stack is going to look like this. How do we get back to the value of the parameter x and y in this case? In other words, somehow I have to implement the actual code of this program. So let's go ahead and take a look at the, I thought I put it here. Well, it's okay. Okay, so we are looking back to just find max instead of find max n. And the first thing we need to do is a compare. Okay, we need to find out where's x, we need to find out where's y, and then do a comparison. How do we do that? How do we find the value of parameter x, and how do we find the value of parameter y? The stack pointer is the only thing, the only clue that we have, okay? Unfortunately, the stack pointer is not pointing directly to x or y. It's close, but not quite, right? So what do we do? What do we do to get to x, and what do we do to get to y? We do arithmetics, right? Okay, we copy the stack pointer to a particular register. We add one, increment, decrement, or something like that, and then we do a dereference. Then we can get to the actual value. Okay. So let's see what we can do with our. Do you want me to use the pseudocode or the actual mnemonics in the toy processor? Mnemonics. Okay. So we'll do the mnemonics here. Okay. So the comparison is going to have to retrieve the value of x, which is just one byte on top of the return value, which is one byte on top of what D is pointing to, and y is the other one. Okay. We are very tight on the number of registers. Okay, so I'm hoping that we have enough to get this done. So we'll see. All right. So the first thing we have to do is to use a CPR to copy register. We want to copy register D to one of the other three registers. At this point, register A has no special meaning because we are not even close to the end of the subroutine. So until the very end of the subroutine, you can use register A as any other registers. Okay, there's no problem of using register A at all. Okay, so we'll just copy register D to register A. And as a comment here, I'll just say that A is now pointing to the return address. Is that notation okay? If I dereference register A, I will find the return address. Okay? Which is not what I want, okay? Because what I want is x, which is just one byte on top of that, okay? So we'll say increment, because we have the increment instruction now, we can just use it. So we can now increment register A, and after the increment, then A is now pointing to parameter x. Is that okay? And we want to put it somewhere because we want to get to some other registers. So we want to do LD instruction. The LD instruction is going to copy a memory location to a particular register. Okay, so we want to specify the register first. We have 4 registers. We have used up 2 already. So we're going to use register B in this case, and indirect A. So that means register B is whatever A is pointing to, which is parameter x. Is that okay?
Why didn't we just use copy register?
Huh?
Why didn't we just use copy register?
Because copy register is because A is not parameter x. A is the address of parameter X. So I need to dereference A to get to the value of the parameter. That's a good question, okay? Because if you just use a CPR, then you'll be copying the address, but not the value of the parameter. Okay, good job. Good question. Very good. Then I will increment A again. So A will now be pointing to parameter Y, and I'll do something like that again. And this time I use register C, like that. So at the end of these operations, C is going to be whatever A is pointing to. At that point, after the increment, is going to be parameter Y. Are we doing okay so far with these instructions and how they relate to the C code? Because that's the most important part, is how do they relate to the C code? Is that okay so far? Okay, all right. So we're going to do the comparison next, because now we have parameter X in register B, parameter Y in register C, so we can now do the actual compare instruction. So we'll do a compare CB, okay? So in other words, we are just doing a subtraction, but without storing the difference somewhere. Yep.
Does increment supposed to increment anything?
Say again?
Does increment instruction supposed to increment anything?
It's supposed to increase the value of the register A by 1. That's part of the questions in the exam, and I implemented that instruction. So the new all.rom has the implementation of that.
Why are you just giving it the value of Y?
Huh?
Are you passing it the register A value of Y?
No, A is, okay, this is what A is, right? Because I make a copy of D to A, so A is originally pointing to the return address. When I add 1 to it, it will point to parameter X.
Oh, I see.
When I add it one more time, it will point to parameter Y.
Yes.
And then the LD instruction is doing the dereference. So we, instead of having the address of the parameter, I actually have the value of the parameter stored in register B and C. Is that okay? All right, okay. So now we need to, I'm just looking at the time, I think we got enough time to finish this. Okay, so now we have a compare, and looking at this comparison, we know that we kind of have to branch if this is not true to the else case. So we will do the usual thing and say that if X is greater than or equal to Y, we just branch, okay? Except we don't have greater than or equal to. We have less than. We can confirm less than with one single conditional branch, but we cannot do greater than or equal to, which means, to save instruction, it is better to do it this way. Because if I do it this way, I can do a JLI to the else label. Okay, we'll put an else label here. Because what this is saying, if you look at these two instructions combined, they're basically saying if C is less than B, then we go to the else label. Well, that only takes care of one particular case. Now in this program, it doesn't really matter, because when they are exactly the same, we can go either way. But in this, but in order to stay true to the code, I have to do this, because this one takes care of the case when B is greater than C. This will take care of the case of when they are the same. So now I'm preserving the exact meaning in the C code. Is that making any sense? Okay. All right. So when we get here, this is our then branch, okay, which is returning a value of the value of Y. Remind me again, how do we return a value, a value?
Storing it
Into register A. Very good. Okay, so that's relatively easy because we just have to do a CPR. Because in this case, we want Y, which is already in register C, so we just CPR CA, and now we are ready to return. Okay, so I'm not following this code directly. I'm doing a return Y in this case. Okay. Can someone remind me how do I return from a subroutine? Two operations, The first one is to retrieve whatever the stack point is pointing to a particular register, and then the second one is to deallocate that space, and then the third one, I guess there are 3 operations, the third one is to branch to whatever that register is. Okay. Since I will have to do it over here again, I have one single unified return point, okay? So I'm just gonna have one single point of return, I'll label it as return. So at this point, okay, and this can just do a JMPI to return, just like that. So at this point, I'm ready to go back to my caller. And to do that, I need to first copy C.cp. I need to do an LD to a particular register. I cannot use register A anymore because register A at this point is meaningful. It is the actual return value. But I have 2 other registers to play with, so that's cool. Just like that. Okay. So B is now the the other way around. B is the return the return address. But after I grab the return address from the stack, that location on the stack is no longer needed, right? Because it has served its purpose. So it is now time to deallocate that byte from the stack. How do we deallocate something from the stack? We do something with the stack pointer. What do we do to the stack pointer? Increment, very good. Okay, so we increment the stack pointer to deallocate that. So we say d plus plus d to deallocate 1 byte, okay? Now that the stack is balanced, because we have used up that byte and we deallocate that byte, it is now to actually go through the jump, and we are using jump B in this case because we are going to continue where B points to. Continue execution to the point that B is pointing to. Is that okay? All right, okay, very good. So now we only have one more thing to deal with, which is the else. That's the other register. So are we doing okay so far with this particular subroutine? Just the subroutine itself, we'll deal with the calling of the subroutine next. Is that okay so far? Okay, all right, cool. Now we need to look at the caller of the subroutine and say, okay, if the subroutine is doing this, what does the caller have to do in order to make use of the subroutine, that to compute the maximum of 2 particular things? So we look at, I'm just going to put the main here just so that it looks like it resembles the main program here. So in the main, let's just say that we want to find max 23 and 61. Okay, we know the answer right away, but we just want to kind of go through the motion to know what to do when we try to call a subroutine like that. Okay. All right. So we have to go all the way back first because we want to look at how the stack is supposed to be structured by the time we get to the subroutine. We need to put y first on the stack, then x, and then the return address. Okay. Very good. So we know second parameter, first parameter, and then the return address. How do we get 61 on the stack?
Put it into some register and then register to register.
Okay, all right, so we put it into a register first. Remember not to mess up register D because that's our stack pointer. So we say LDI, A is fine, A has no special meaning at this point, so we can just use register A. And then what do we do? How do we store something on the stack? What are the steps that we have to go through? Allocate first. Very good. Okay, so we have to allocate the space on the stack first. So we have to decrement the stack pointer in order to allocate space. So always remember to allocate first before you store. And then what do we do? Just store register A to wherever D is pointing to. Very good. Okay, so we do ST for store. Store to whatever D is pointing to. The parentheses indicate D reference, and we store whatever A has to where D is pointing to. So this is basically saying whatever the stack point is pointing to gets 61. Okay, that's one parameter. Let's do it to the other parameter. LDIA 23 decrement the stack pointer again, and then store A also, to wherever the stack pointer points to. Is that okay? So this is how you pass parameters through the stack to a subroutine. Are we still doing okay so far? Okay. And then what is left that we have to do is to call the subroutine. So to call a subroutine, we have to first establish a label, which is the return address. Okay, so this is a return address, and we'll continue with a halt instruction. Okay, there's nothing to do after this point. Okay, so knowing that we have to return to RET-ADDR as a label, what do we have to do? It's the same thing as these operations, except we're not doing 23. We're doing this label RET-ADDR, right? Okay, so we'll do exactly that, LDIA RET-ADDR. So register A is the address of the halt instruction. Decrement the stack pointer to allocate that 1 byte on stack, and then store whatever register A has on the stack. This is how we store the return address on the stack. But that's only one half of the call instruction. What is the other half of the call instruction? We have to continue execution in the subroutine. And how do we do that? Jump I, JMP to the subroutine, which has a name of find max. Just like that. We have the whole program now. Now, this does not include the initialization of the stack pointer, because in a regular C program, by the time main has control, the stack pointer is already initialized. So we don't have to worry about that in a regular C program. But this is not a C program. This is an assembly program that has no operating system to help initialize the stack pointer. So we will have to do that. Do you guys remember how to initialize the stack pointer so that it points to the highest possible location in RAM? Okay, we can load D with a 0, we can do a sub DD, both of these will do the same thing. Okay, very good. So I'm just going to do the more obvious one, which takes up 1 more byte. It's a 2-byte instruction that's supposed to do 1. Okay, so when we're using our toy processor, this part has to be at the very beginning, so we have to cut and paste it. So we have to cut this and paste it over here, because the execution always starts with location 0. Okay, that's the way the toy processor works. All right, what do you think? Shall we give it a try? Okay, so we Control A, Control C, go to the spreadsheet, the assembler spreadsheet, and this is the source. Great. Okay, so just Control V, paste it. Okay, there we go. This is our. Is that a new program? No, that's not. Control V. There we go. So this is our new program. It goes through all the computation. Scroll down, make sure we don't see any errors in column B, because if it spots any problem, it will show up. And then we switch to the RAM file tab and just download as CSV. We'll store it as findmax.csv. There we go. And now we have to start up the logic sim. We'll start up the processor. So we have java-jar. And the processor. This is the WDPC2, which has the increment decrement mechanism. ALU, branch bank. There we go. So we'll go ahead and reset it first, just to make sure everything is in the default reset state. And then we load the RAM image, which is called findmax.scv. CSV. There we go. We got the program in. If we feel particularly confident, we can just run it until we get to the halt instruction. If we don't feel particularly confident, it's always good to kind of turn on the logging, because if it doesn't behave, we have some clue as to why it is not working. Several registers are particularly useful. When you go to the register bank, register D, which is the stack pointer, is definitely useful in this case, so we want to copy that. The last few locations on the stack are also useful because we know that we're going to use up 3 locations on the stack. One for Y, one for X, and one for the return address. So it doesn't hurt to put those onto the watch list so that if anything changes with those locations, we'll see it. So we go back to here, go to RAM, and then we just go all the way down to the last 3 locations. So we want to monitor location 253, 254, as well as 255. Okay. If you also want to kind of track the execution of the program itself, the PC or the program counter can be very useful. Okay, so we can put that on the list too. So those are the kind of the usual things that you want to monitor when you're running a debugging program, because the stack definitely useful. Okay, the stack pointer you have to track. Are you decrementing, incrementing, and so on? The program counter, very useful as well, because you want to know, okay, where am I executing? Okay, at least you'll be able to trace your way and go like, oh, it went here, and then went here, and then went here. Okay. Memory locations on the stack also useful, because you want to know what did you put on the stack. Did I put 63 on the stack? Did I put all the right values on the stack? So those are the things that I want to kind of monitor. And once I put these items here, you can also use file if you want to. You can enable file output. So this way it is not stored inside Logisim, it is actually output to a file. So you can use a text editor and whatnot to process that file. You can search for things and whatnot. So that can be useful as well. I'm just going to use a table for now. Okay. So we'll go ahead and cross all of our fingers and give it a shot. That doesn't seem right to me. Oh, okay. We got to the halt instruction. That's kind of encouraging. Instead of going to some la-la land somewhere, okay? This is not going to give you a segmentation fault. Okay, because there's no, it's not running in protected mode where it goes like, hey, you're going to a location you're not supposed to. No, all 256 locations are fine. Do whatever you want. Okay, so we want to check register A and see whether it is the maximum of those 2 particular values. And of course, I cannot remember which 2 values we were using. So we want to look up the, where did I put that? Well, we know it's going to be here, right? In the source. So we know that we are trying to find the maximum of 61 versus 23, which should be 61. So we are expecting 61 in register A. So we go back to the Logisim, we go to the register bank, and then we say, look at register A, it has a value of 1, 2, which is not 61.
Maybe it's 61 in like hexadecimal.
No. 1, 2 is what? 1, 2 is 18.
Yeah.
And the program does not even have 18 as a value. Okay, so it doesn't quite work the way we want it to. Okay, so now we can look into the, well, we have a little bit more time, so I'm gonna use a little more time here, and then I'll finish the debugging in the lab, okay? Because I can run it again, store the values in in the file, and then we will debug it that way. But when we go through the logging, we look at the table, and then we look at all of these things. This is the last location. So we want to look at these locations first, and we don't see any changes to those locations. Or maybe it doesn't log everything. That is suspicious. Because we are not seeing any changes to the RAM locations. Location 255 never got changed. And then this register, which is register D, that's our stack pointer, is changed, but it is not changed correctly either. It is changed. You know what? I think the increment and the decrement instructions were not implemented in this ROM file. That probably is why. That would definitely make it not work, right? Let's see. The last time I thought I checked it. 100. Okay, let's check this. Edit content. And those are E series, right? That's the E series. Yeah. E and D. And because E, and then we have identical registers, so we have E0.
I feel like E50 is the same.
And then E5, right?
Yeah, E5 is not the same as last time.
Is that correct?
I think that was.
Seems correct to me.
Yeah.
So E5, E6, E7. Okay, E6 and E7 should be pretty close, and then E5 should be different. I don't think they're different enough. That may not be the correct one. I think we wrote down what they're supposed to be on the in the previous class. So I think I got the wrong content. So the microcode itself is wrong. So there's no way the program is going to work correctly in this case. But you can see how the log is useful, because I can just go through the log and go like, hey, register D is not even going to FF or 255, which is when it gets to the decrement instruction, it should go to FF. It did not. So that's the indication right away. Go like, okay, the instruction itself is not implemented correctly. So I have to go back and check it. Right. Well, we're running out of time out of the lecture, so what I'll do is I'm going to bring this to the lab, and I will finish this program in the lab. If you want to watch me do it, that's fine. If you want to continue to ask questions in the process, that's good. I think it is valuable in a way that you can see how I debug the program, which may be something that you will have to do when you write your particular program. So from that perspective, it might be a useful experience. Yep.
When we turn in the homework assignment, are we submitting to you the CSV that's been exported from?
No, you just turn in the source code.
Okay.
Yep, just turn in the source code, and that's fine. All right, so let me stop the recorder, collect all my stuff, and then move on to the lab.